one team. I would hope there would be more than one team. Okay, Benito, I hope you enjoyed this lecture. Okay, so again, it's another day of, yeah, we already know all this stuff, so let's just practice it. So basically the rest of the unit, with the exception of solubility, it's 8, 6, 7, 8, 9. Yeah, 8, 7, 8, 8, 8, 9, 8, 10. It's all about buffers and then doing titrations. So you learned about Henderson-Hasselbalch. And again, the Henderson-Hasselbalch equation is what happens when you squish the pKa, pKb square into the H3O OH square. You get that. Take the logarithm of a product and you get the sum of the logarithms. So again, you use Henderson-Hasselbalch a bunch. That's on the formula chart. The OH one is not, but you can still use it. You can also convert all your pKb's and POH's into pH and pKa's and use Henderson-Hasselbalch. You know what I mean by that? So if you're trying to do a base and you're given a pKb, you can turn that into a pKa just by dividing by 10 to the negative 14, or subtract 14. Okay, and you can do that too. So the OH, obviously, it's BH plus over B. So, and when they are exactly the same, their equal logarithm of 1 is 0, so the pH equals the pKb, just what you've been doing a million times. So now it's just a matter of plugging the numbers in. Now, this is usually how you're going to encounter a buffer question. The exercise will be a buffer is created by, you're going to add a salt of the anion. So this is Na, I don't know why I did the Na back there, but this is the A minus here. This is the HA. So you're going to put the salt of the anion in with the weak acid. That's going to give you the backside of Henderson-Hasselbalch. And then you're going to get the Ka or the pKa of that acid and solve for the pH. So let's go ahead and bang that one out. So buffer solution is created by dissolving 87.5 grams of sodium acetate. Again, CH3CoO is once again the acetic acid, one of the 3 ways they show acetic acid. And it's a Ka that every chemistry AP teacher has memorized, 1.8 times the negative 5. So 87.5 grams of sodium acetate is added to 1 liter of 1 molar acetic acid. And we're going to pretend that the volume does not change, which is pretty good because we're adding a solid, it goes into the water. Find the pH. So go ahead and work this one out. If you get hung up, let me know.
You want a calculator? Yeah.
I will wait a little bit, but I'll put my work on the board and see if your work equals my work, or is similar to my work.
with negative log. So negative log of that times, and then it's just negative or minus the log of 1 over
How many moles of sodium acetate did we add?
1 point. Yeah, it's 1.
That's exactly 1
Yeah,
mole?
it's like 1.00.
Okay,
So yeah.
whatever. Yeah. So again, so it's going to be 1 mole in 1 liter, so it's going to be 1 over 1. Oh, sorry. Oop, there we go. Plus 0. So the negative logarithm of k of 1.8 times on negative 9 is
Like
8.7.
8.74?
I got 4.7.
Yeah, 4.7. So again, what they've made is once again the perfect buffer where you have the same concentration of the acetate ion, the A minus, and the acetic acid, HA, 1 molar and 1 molar.
Yeah.
So we got a logarithm of 1, which is 0. So the pH equals to pKa.
Yeah.
Cool with this?
Yeah.
Okay. Let's move on to something where the concentrations are not the same, I hope. Oop. All right, here we go. So more buffer solution. Hey, look, it's a basic buffer. Woo-hoo. So basic buffers work exactly the same way. It's just now you're using the conjugate base. Oh, I thought, oh, not that one. This one. There we go. Doodle-doo. Okay. Anyway, so 75 grams of ammonium chloride. This is our BH plus, and that liter of that concentration. This is our NH3. KB is given, and pH. All we care about is pH. Okay, cool. So the author in this case wants us to swap everything into the acidic Henderson-Hasselbalch. Let's do it both ways. So first, let's do the basic Henderson-Hasselbalch, which is POH equals PKB plus the logarithm of BH plus over, oh, that's just B, over B. Now, one of the really important things is notice that it's giving you this volume and this concentration. We're adding a solid, so we're assuming that the volume doesn't change, so our concentration is not going to change, but be really careful that you don't take the moles over 1 liter because it's 1.14 liters. Is what I said just makes sense? So in the previous exercise, we found out how many moles of the other thing is, and we divided by 1 because it was just, we needed molarity. In this case, the volume is not 1, it's 1.15. So what we're going to do is, how many moles of ammonium chloride is 75 grams?
Four.
1.4?
Yeah.
So 1.4 in over 1.15 liters. This is going to give us our concentration of our pH plus.
1.2.
Really? It's 1.2 again? Oh, come on. I thought for sure this would be different. Okay, whatever. So once again, this falls out, and our POH is the logarithm of our PKB.
No, it's 1.4 divided by 1.5. 1.22.
Am I 1.22?
It's like it's.
Hey, let's pretend it's not. Okay, cool. Let's take care of the rounding issue. So let's make that 1.22. That will be fine. There we go. So it'll be a tiny change. Whee. a tiny change.
Negative 0.01 for that logarithm.
Negative 0.01.
2, I guess it was 2.
2. All right. And the negative logarithm of 1.8 times 10 to the negative 4, you say it was 4.74?
Yeah.
Okay, so this is 4.74 plus 0.012. So 4.75 is the KB, which is, or sorry, PKB, which is equal to the POH in this case. So if that's the POH, what's the pH? .25, which makes sense because we are buffering a weak base with its conjugate acid. So the pH should be in the basic range. Cool. Now, if we wanted to use the Henderson-Hasselbalch that's in the book, we would go, or on the formula chart, we go pH equals PKB, pKa plus the logarithm of the A minus over DHA. And the reason I don't like to do this is because you have to take the KB and first turn it into a pKa, which means you got to divide it by 10 to the negative 14, then take the negative logarithm of it. Yuck. And then these numbers, where do you get A minus? Yeah. It's basically this flipped over. So I don't do that. I do the basic version of the Henderson-Hasselbalch when I'm given a base. All right, can we move forward? Textbooks like, well, just give up the acid. Why would you want to do that? All right. Fusion buffer solution. Nope, not do that. Which buffer will experience the greatest decrease? Ooh, this is a good question. Which buffer will experience the greatest decrease in pH, more acidic, when 500 milliliters of hydrochloric acid is added to each of the following? The first solution is a 0.5 molar sodium fluoride solution and hydrogen fluoride solution. Right. Okay. It's a previous exercise. Okay. Yeah, we'll get that in the lab. Here's the important thing. Buffers work by absorbing extra protons when acids are added, or releasing extra protons when bases are added. And the reason the pH doesn't move very much is because the ratio is a logarithm. It's a logarithm of A minus over HA. Which means if you had 10 times more A minus and 10 times less HA, this would only be a logarithm difference of 2. So by making one thing 10 times more concentrated, the other thing 10 times less concentrated, this is 100. So it only changes the pH by 2. Okay. That's why buffers do what they do. So, and again, it is possible to exceed the buffer capacity of the solution, meaning you've added so much H plus or you've taken away so much H plus that you've basically consumed all of the weak acid that was there or consumed all the weak base that was there. But that's pretty rare. Let me get to a good exercise. Which buffer will experience the greatest? Yeah, okay. Okay, here's the other thing. 0.15, 1.5. This is lab 16 we're going to be doing when we get back from spring break. The first solution is 0.5 and 0.5. It should make sense that the more concentrated buffer can absorb more protons or give off more protons. So if you got a 0.5 molar NaF and a 0.5 molar HF, and you had a 1.5 molar NaF and a 1.5 molar HF, will their initial pHs be the same? Think about that. Let's see if I can squish my screen a little bit. Here we go. So one of the solutions is 1.5 and 1.5, and one of the solutions is 0.5 and 0.5. Will their initial pHs be the same?
Yeah. Yeah, it should be. Oh, no.
So here's solution 1, here's solution 2. Solution 1 has a concentration of 0.5 over 0.5. Solution 2 has a concentration of 1.5 over 1.5. Will they have the same initial pH?
Yes.
Yeah, they're the same chemicals. So the pH is still equal to pKa. pH is still equal to pKa because in both cases the ratios are exactly the same. In this case, 1. 1. So they will have the same initial pH, but the more concentrated buffer will be able to absorb more protons or release more protons. Therefore, it will have a larger buffer capacity. Make sense? I almost feel like lab 16 is a waste of time, but that's what we're going to do in lab 16. We're going to test a 1 molar buffer versus a 0.1 molar buffer and look at the pH change and we add stuff. But, you know, yes. Okay, if you're comfortable with that idea, give me a thumbs up. Because that will be tested, the idea that you have more concentrated buffers. All right, what a good exercise. Exercise 1, exercise 2, net ionic equation. Additive solution, hydrofluoric acid. Oh, this was on a previous exercise, so I just want to mention it. Just a quick review. When we have a strong acid and a strong base, the net ionic equation is what? Strong acid, strong base. What's the net ionic equation?
H plus, or HA plus B.
Yeah, the net ionic equation is always just that. That's it. For a strong acid and a strong base, the net ionic equation is always just H plus OH makes H2O. If you want to throw in an H3, if you want to replace this with H3O plus OH minus, just please make sure you actually do 2 H2O. Some people do this instead. I prefer this, but they're both equivalent. Just make sure you're balanced. That is for a strong acid, strong base. However, for a weak acid, you need to write the entire thing. Since HF is a weak acid, we're going to write HF plus, so we're doing sodium hydroxide and hydrofluoric acid, HF plus OH minus, and that is going to be in equilibrium with F minus plus H2O. You got to show the whole weak acid.
A weak acid, strong base.
Yes, in this case, a weak acid, strong base. I've never seen them do a weak acid, weak base net ionic equation. This is what they test about 3 times out of 5. But more than half the time, they just do this very thing. They love HF because they love testing. They will always test every year, do you realize HF is a weak acid? Test that every year. Sometimes they care about why, but they always care that you know. Okay, indicators. So we talked about indicators before. When we're doing a titration, the point at which MAVA equals MBVB, the moles of A equals the moles of B, that's called the equivalence point. The end point is the point where an indicator changes color. So classically, one of the ones we use is phenolphthalein. It's a red compound in the presence of a base, and a clear color, a colorless compound in the presence of an acid. But its endpoint is actually like 8.5. It's not 7. So there is a difference between endpoint and equivalence point. Yeah, color changes. I don't really care that much about that. Okay, choosing an indicator. You need to choose an indicator that has an endpoint near what you anticipate your equivalence point to be. This is a big one. Okay. You need to choose an indicator that has an endpoint or an endpoint range that is near what your equivalent point is expected to be. Now, in your exercises, they give you a whole bunch like this. In the multiple choice, they usually give you around 4, around 7, around 9. Or around 3, around 7, around 11. So there's not a lot of nuance. But if you are titrating a strong acid, this is a question for you. If you are titrating a strong acid and a strong base, which indicator should you choose of this list of 5?
Blue.
Yeah. You're going to choose this one. So if you're of a strong acid and you're titrating with a strong base, you would expect the equivalence point to be around 7. So bromoethynol blue is your best bet.
Is it brown? Is it brown fine?
Yeah. I've always heard it as bromoethynol, bromocreosol, but maybe the authors from a different part of the country would have an extra O. Anyway, this is one that pronounces methylamine as methylamine. Maybe it's from New Mexico. I got the methylamine. It's like, oh, methylamine. Anyway, you've heard my spiel about Breaking Bad. The MacGuffin. You know what a MacGuffin is?
Yes.
A MacGuffin is something that you have to get. It's the one ring. The MacGuffin is the goal of the show. The MacGuffin in Breaking Bad is methylamine. I've got the methylamine, and you can't make your meth without it. It's like, no. Methylamine is this. It's NH2CH3 methylamine. We could make it right now with what we have in the room. You could make it in your kitchen. It's not hard to make. It's certainly not a controlled substance.
Does it have effects?
It'll poison you. All you do is run a natural gas, like methane. You just run methane and ammonia together at high pressure, and that's what drips out. Boom.
So when they're making meth, they're just making that or no?
They needed a MacGuffin that people could understand. So the MacGuffin was methylamine. But honestly, he'd be like, oh, I need methylamine? I'll go make it right now. We could make gallons of this stuff by the end of the day.
After the AP test, are you going to spend that like a couple weeks before the end of the school year teaching us how to cook meth?
No. It's, somebody asked me a couple months ago, it's like, okay, as a chemistry teacher, could you make meth? And I said, honestly, yes, but not in any concentration, and not in any purity that would be safe. It's like, I could make meth that would kill you. Put you in a coma. Okay, so now let's do, what if we're going to be titrating a weak acid with a strong base? A weak acid with a strong base. Which indicators would be a good ones to use? I'm sorry? Yeah, phenolphthalein and alizarin yellow. So if we're going to titrate a weak acid with a strong base, we know that the equivalence point is going to be basic because a strong base leaves a negligible acid and a weak acid leaves a weak base. So we would choose these guys. We would choose something in the basic range. And then, of course, if we were titrating a strong acid with a weak base, we would choose these guys because we realize that a strong acid leaves a negligible base and a weak base leaves a weak acid, so the equivalence point is going to end up being acidic. That's usually as far as the AP will test. In your exercises, though, you want to match the pKa to whatever your indicator is. So if you're using an indicator, if you're using an acid that has a pKa of 5, you want to shoot for an indicator that's around 5. That's just how it works. Okay. But again, I've never seen that. Never seen that tested with that level of granularity. It's usually acid, base, or neutral. Moving on. Choosing an indicator. There's strong acid, strong base. Equivalence point. Yeah, bromothymol blue. Indicator, weak acid, strong base. Something that's basic. Moving on, moving on. More stuff, and we are done. Okay. Now it's just math. All right, we're going to do this last one. All right. Okay. A solution of hydrazine, N2H4, has a pH of 11. Why is hydrazine a weak base?
Because it has the nitrogen pull.
Exactly. Exactly. It is the unshared pairs on the nitrogen atom that strongly attract the proton, making it a weak base. It's a fairly robust weak base, but it's still a weak base. Is that clear? Talked about it yesterday, so I want to make sure we're comfortable with that. So it is the unshared pairs on the nitrogen that attract the proton, making it a weak base. So it's got a solution of a pH of 11. The pKb of that weak base is 6.05. Is the N2H4 greater than N2H5, less than N2H5, or equal to N2H5? How would I solve that? This is such an excellent exercise.
And you do with the pH and the pKb, you can find the negative logarithm. I said the logarithm of pH over.
Okay.
And then if it's greater or less than 1, you know which one's greater.
I think you're saying we should use the Henderson-Hasselbalch equation and solve for BH plus over B.
Yeah.
That's what we're going to do. All right, so we're going to say we got POH equals PKB plus the logarithm of our BH plus over our B. In other words, specifically, our POH, which is our POH is what? Our pH is 11, our POH is 3. So our POH is 3.0, and our PKB is 6.05. Thanks for that. Don't have to do any math with that. Plus the logarithm, and we need to solve for this ratio. Do I need to solve for the actual concentrations?
No.
No. I just need to know if my logarithm of that ratio is positive or negative. If it's positive, then the numerator is bigger. If it's negative, the denominator is bigger. Well, what happened here? What is the value of this whole thing? It's negative 3. Let's just make it 3.0. 3.0, sorry, 3.05. So the logarithm is negative, which means which side of the fraction is bigger? The denominator. So it is NH4 is greater than NH5. Is that clear? I'm kind of fast. So is that clear what happened?
Yeah.
Okay.
Is the other one just like an acid? Right, part 1. Right now. So no, just the one on the left.
I'm not even seeing the difference.
I didn't say.
pH of 11 is 7.5. Is it greater than what? I don't even see a difference.
All right.
I don't know. Maybe there's a difference. I'm just not seeing it, but I don't care because we can move forward.
The logarithm is negative. So that means that yeah.
All right. Refresh.
Power is less than 1.
With a tiny amount of time, let's look at some exercises to work on, and then you can be released. Okay. So 2, 12, 14, 18. Number 2, just the
Yeah.
concentration increase.
It's like 10 to the power
Um,
negative 1 is 1 over 10.
So this is just a
That means it's 1.
this is a throwback to common ion. So basically, just like, hey, the common ion is the next unit. So we're going to talk about that. If sodium chloride is added to a liter of a saturated solution of lead chloride, does the concentration of the lead increase, decrease, or remain the same? Again, it's just a throwback to equilibrium. Take a look. Make a decision. Okay. Who says that in the saturated solution of lead chloride, when sodium chloride is added, the lead concentration increases? Who says the lead concentration decreases? Who says the lead concentration doesn't change? And this is why it's here. Okay, so remember, you have a KSP, in this case of PbCl2, and that KSP is equal to the Pb2 plus concentration times the Cl concentration, that quantity squared. And it's saturated, so that's some number. And then you add some sodium chloride as a, what do we call it when we add a single ion that matches something in equilibrium? Common ion. So we're going to add common ion, which means the stress to the system is an increased concentration of chlorine, which forces the equilibrium up and over the equal sign. So we have PbCl2 in equilibrium with Pb2 plus 2Cl minus the stress is extra chlorine. We're going to force the equilibrium towards the products. That means our end product, our KSP, is not going to change because the temperature hasn't changed. What will change is we're going to have a lot more Cl, which means we numerically have to have a lot less Pb. Common ion stuff. Are we comfortable with this? This is the next unit. What we do tomorrow would be like, this is another more easy stuff. What did I say? 4. Find the pKa values. You could take the negative logarithm. And 12. Yeah. Concentration of that is 200 plus pH. This is Henderson-Hasselbalch. Are you comfortable doing the math of Henderson-Hasselbalch?
Yeah.
Cool. Moving on. Buffer solution was created by that and that. Final solution was that. Which species? This is exactly like we did the last one. So there's the pH, there's the pKa. Is the logarithm term positive or negative? If it's positive, the numerator is bigger. If it's negative, the denominator is bigger. And I think that's pretty much it. Yeah. All right. You can use the remainder 10 minutes to do whatever you want to do. Hopefully you had some fun roboting.
You missed the
Bye,
helicopter,
Bennett.
Bennett.
I'm sorry, what?
They had a